Today we are going to discuss preparations of aldehydes and ketones. So let's read from the book. Some important methods for the preparation of aldehydes and ketones are as follows. First method is given the oxidation of alcohols. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols respectively. That is already discussed in the chapter 7. So let's read from chapter 7. So here it is given CrO3 in anhydrous medium is used as oxidizing agent for the isolation of aldehyde. So RCH2OH, this is primary alcohol. When primary alcohol undergo oxidation in presence of CrO3, it gives aldehyde. The another better reagent for the oxidation of primary alcohol to aldehyde in a good yield is pyridinium chlorochromate. The other name is PCC. It is a complex of chromium trioxide with pyridine and HCl. So here there is another example is given. It is again primary alcohol. This carbon is primary, so the alcohol is also primary alcohol. When it undergo oxidation with PCC, it gives aldehyde without disturbing the double bond present in the molecule. Secondary alcohol are oxidized to ketone by chromic anhydride, which is the same reagent used for the oxidation of primary alcohol to aldehyde. When the alcohol is secondary alcohol, you will get ketone. While tertiary alcohols do not undergo oxidation reaction. Now get back to the chapter of aldehyde. The second method is given dehydrogenation of alcohols. The method is suitable for the volatile alcohol and it is of industrial application. In this method, alcohol vapors are passed over heavy metal catalyst like silver or copper. Primary and secondary alcohols give aldehyde and ketones respectively. This is also discussed in chapter 7. So again, let's open chapter 7. Here it is given the vapors of primary or secondary alcohol passed over heated copper at 573 Kelvin. Dehydrogenation takes place and an aldehyde or ketone is formed while tertiary alcohol undergo dehydration. So let's examine these examples. Here, this is the primary alcohol. When it is heated over copper, you will get aldehyde. And here, this is secondary alcohol. When it passes over heated copper, it gives ketone. And here there is tertiary alcohol. When it passed over copper, it undergo dehydration, means the removal of water molecule, and it results in alkene. While primary and secondary alcohol undergo dehydration, means the removal of hydrogen, and results in aldehyde or ketone. Now get back to the chapter of aldehyde. Third method is given from hydrocarbons. The first method is given by ozonolysis of alkenes. As we know, ozonolysis of alkene followed by the reaction with zinc dust and water gives aldehyde, ketone or a mixture of both depending on the substitution pattern of alkene. This is discussed in chapter 9 of 11th standard. So let's open chapter 9 of 11th standard. Here ozonolysis is given in the hydrocarbon chapter. So let's read from the book. Ozonolysis of alkene involves the addition of ozone molecule to alkene and form ozonoid. And then the cleavage of ozonoid by zinc and water to smaller molecules. This reaction is highly useful in detecting the position of double bond in alkene or other unsaturated compounds. Let's quickly revise the reactions. So here I have taken the example of propene, which is given here already. Here CH3 single bond CH double bond CH2. And the another example I am going to take substituted propene. So here this is CH3 single bond C CH3 double bond CH2. When this first molecule undergo ozonolysis, this is O3 and you have to draw ozonoid. So when you draw the ozonoid, you will get CH3, this carbon, this is bonded to hydrogen, and this is another carbon CH2. Now you have to attach oxygen. So here oxygen will make bond with both the carbons, and here second oxygen, this is third oxygen, and that's how you will form ozonoid. In the same way, you can draw the ozonoid for the second alkene. Here, this is carbon. It is bonded to CH3 on both the sides. This is CH3 and here it is CH2. Now attach oxygen. So here, that's how you can attach ozone O3, and this is the ozonoid. Now this ozonoid undergo cleavage. So here you have to break all these bonds where this line passes through. So this reaction takes place in presence of zinc dust and water. And you will get the product. Here you will get C, it is bonded to CH3. One side it is bonded to H, and you will get double bond with oxygen. Another product you will get oxygen double bond carbon, and on both the sides it is bonded to hydrogen. So here you can see this is an aldehyde, this is also an aldehyde. Now draw the product of this alkene. So here carbon, it is bonded to CH3 on both the sides, and now it will get double bond with the oxygen plus oxygen double bond carbon, and here it is bonded to hydrogens. So here when you see, this is again aldehyde, but this is ketone. So in case of substituted alkene, you will get the mixture of product ketone or aldehyde, or you may get both the ketones. But the alkene is less substituted, then you will get aldehydes. Now get back to the chapter of aldehyde. Next reaction is given the hydration of alkynes, addition of water to ethine in presence of H2SO4 and HgSO4 gives acetaldehyde. All other alkenes give ketone in this reaction. It is also discussed in chapter 9 of 11th standard. So let's open the chapter 9 of 11th standard. Here we need to find where it is given. So here it is given. So let's read from the book. Like alkanes and alkenes, alkynes also immiscible and do not react with water. However, one molecule of water adds to alkyne on warming with mercuric sulfate and dilute sulfuric acid. So when one molecule of water adds to alkyne in presence of dilute sulfuric acid and HgSO4 at 333 Kelvin temperature, it gives carbonyl compounds. Let's quickly revise this reaction. So here this is ethine. Here this is ethine. So let's draw CH triple bond CH, and here you have to add water molecule. So H plus and OH negative. As ethine is symmetrical, there is no need to follow Markovnikov rule. You can add H plus to either of the carbon. So here you will get CH. If I add hydrogen to this carbon, CH, and I am going to attach OH to this carbon. Now this molecule has double bond and OH. So this is enol. So this molecule is enol, and when it undergo isomerization, you will get the molecule CH, H, H, single bond C, H, double bond. So this is aldehyde. This is an aldehyde. Let's take another example. This is CH3 C, triple bond, C, single bond, H. Now add water to it. So H plus and OH negative. Now you have to follow MK rule. As this alkyne is unsymmetric, so negative part of the reagent goes to the carbon which has less number of hydrogen. So it will get attached to the second carbon and H plus will get attached to the first carbon. So here you will get CH3, C, double bond, CH. Now here you have to attach OH and H will get attached to the first carbon. Now again this is enol, double bond and OH. So this is enol. So when it undergo isomerization, you will get, so it will undergo isomerization and here you will get CH3 single bond C, double bond O, single bond CH3. So here you will get ketone. So only in case of ethyne you will get aldehyde, otherwise you will get ketones. The same thing is given here also. When propine react with water molecule, after isomerization you will get propanone. Now get back to the aldehyde chapter. Now come to the preparations of aldehyde. Till we have discussed the mixed method for the preparation of aldehyde and ketones. Now we are going to focus on the preparation methods of aldehyde alone. First method is given from acyl chloride or acid chloride. Acyl chloride is hydrogenated over catalyst, palladium on barium sulfate. The reaction is called as Rosenmund reduction reaction. This is acyl chloride group. When chlorine is bonded to carbonyl carbon, it is called as acyl chloride. When it undergo hydrogenation in presence of palladium and BaSO4, it converts to aldehyde. And this reaction is called as Rosenmund reduction reaction. Now come to the next reaction from nitriles and esters. Nitriles are reduced to corresponding imine with the stannous chloride in presence of hydrochloric acid, which on hydrolysis gives corresponding aldehyde. This reaction is called as Stephan reaction. So let's try to understand this reaction. So here it is given R. R can be any alkyl group and this is carbon. It is triply bonded to nitrogen. This is called as nitrile. So this is nitrile. When it undergo reduction in presence of SnCl2 and HCl, it reduces to imine R, C, H, double bond NH. Double bond NH is called as imine. So it is called as imine. If I remind you, amine is single bond NH2. NH is there and nitrogen is doubly bonded to carbon is called as imine. When this imine undergo hydrolysis in presence of HCl, means the medium is acidic. So here I am going to write H3O+. When it undergo hydrolysis, this bond will break and here you will get R, C, H double bond O. So this is aldehyde. So that's how you will get aldehyde by the reduction of nitrile. Now let's read from the book. Alternatively, nitriles are selectively reduced by diisobutyl aluminium hydride, or it is also known as dibyl H, to imine followed by the hydrolysis to aldehyde. So dibyl is also working in the same way as stannous chloride and HCl work. But it is more specific as it reduces only nitrile to aldehyde without affecting double bond present in the molecule. As in this example, there is double bond present in the molecule, but dibyl H only reduces nitrile to aldehyde without affecting the double bond present in the molecule. Similarly, esters also reduces to aldehyde with dibyl H. So this is the ester. So this is the ester functional group. When it reduces with double H, it reduces to aldehyde. Next method is from hydrocarbons. Aromatic aldehyde, benzaldehyde and its derivative are prepared from aromatic hydrocarbons by the following methods. First method is given the oxidation of methyl benzene. Strong oxidizing agent oxidizes toluene and its derivative to benzoic acid. However, it is possible to stop the oxidation at the aldehyde state with suitable reagent that convert methyl group to intermediate that is difficult to oxidize further. The following methods are used for this purpose. First method is use of chromyl chloride. The chromium chloride oxidizes methyl group to chromium complex, which on hydrolysis gives corresponding benzaldehyde. So here this is toluene. When it reacts with chromyl chloride, and here this is CS2. CS2 is carbon disulfide. This is non-polar solvent. It is a non-polar solvent. On the reaction of chromyl chloride with chromium, it make a complex with a methyl group and form chromium complex. Here this is the chromium complex. So let's learn how to draw the structure or how to remember it. So let's draw the structure. Here this is toluene. Benzene attached to CH3 is called as toluene. So this is carbon and it is bonded to 3 hydrogens. Now there is chromium. Double bond oxygen and here double bond oxygen, and there are 2 chlorines. In a concerted manner, one of the oxygen will abstract hydrogen from the toluene. One of the oxygen will make bond at the same time with the carbon. So here you will get the product. So this is benzene and it is bonded to CH2. Now this will make bond with the oxygen. Here Cr, here it is bonded to OH, and on the other side there are 2 chlorines. So again, when the same reaction takes place, you will get this is CH this time, and there are 2 molecules will get attached. So here I can write O, Cr, OH, Cl2 whole twice. So that's how this chromium complex has formed. When it undergo hydrolysis, so when it undergo hydrolysis, this bond will break and it result in the formation of benzaldehyde. So let's draw the structure of benzaldehyde after the hydrolysis. So after the hydrolysis, H3O+, here you will get benzaldehyde. This is CH double bond O. This is benzaldehyde. That's how by the reaction of chromyl chloride and toluene you will get benzaldehyde. And this is called as Etard reaction. Now come to the next reaction. The next reaction is the use of chromic oxide that we have already discussed by the formation of aldehyde and ketones from alcohol. Toluene or substituted toluene is converted to benzylidene diacetate on heating with chromic oxide in acetic anhydride. The benzylidene diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. So here, this is the toluene. When it reacts with chromic oxide in presence of acetic anhydride, this is acetic anhydride. When they all are heated together, it results in the formation of benzylidene diacetate. This is benzylidene diacetate. And when this benzylidene diacetate undergo hydrolysis, it results in the formation of benzaldehyde. In the same way as we draw the chromium complex, you can also draw the structure of benzylidene diacid. So let's try to understand how to draw the structure of benzylidene diacetate. So this is toluene. Benzene with CH3 is called as toluene. When it reacts with acetic anhydride is CH3, C double bond O, O, C double bond O, CH3. Here you have to break this one of the bond and remove one of the hydrogen from here and just attach the remaining molecule with CH2. So here you will get CH2 and here you have to attach with O, C double bond O, CH3. And again you have to remove one of the hydrogen from here and you will get the structure of benzylidene diacetate. So it is CH and here O, C double bond O, CH3 whole twice. So this is the benzylidene diacetate when it undergo hydrolysis. So when it undergo hydrolysis, here this bond will break and you will get benzaldehyde. Now come to the next reaction by side chain chlorination followed by hydrolysis. The side chain chlorination of toluene gives benzyl chloride, which on hydrolysis gives benzaldehyde. It is the commercial method of manufacturing of benzaldehyde. This is toluene. When it is exposed to chlorine in presence of UV light, it undergo free radical substitution reaction and it affects on the side chain only. It doesn't affect the benzene, that's why it undergoes side chain chlorination. So when it undergoes side chain chlorination, it forms benzyl chloride and on hydrolysis, it gives benzaldehyde. So this method is used for the commercial preparation of benzaldehyde. Now come to the next reaction. This is the Gatterman-Koch reaction. When benzene or its derivative is heated with carbon monoxide and hydrogen chloride in presence of anhydrous aluminium chloride or cuprous chloride, it gives benzaldehyde or substituted benzaldehyde. And this reaction is known as Gatterman-Koch formylation reaction. It adds formyl group to the benzene. So CHO group is also called as formyl group. So the other name of this reaction is Gatterman-Koch formylation reaction. Here you have to remember the set of reagent. Which reagent is used for the Gatterman-Koch formylation reaction? This AlCl3 and CuCl act as a Lewis acid. And it results in the formation of formyl cation, which act as an electrophile for benzene. And that's how it results in the formation of benzaldehyde. So let's try to understand how this reaction takes place. So this is benzene and this is carbon monoxide. Carbon monoxide has carbon, it has lone pair of electron and it is triply bonded to oxygen. So this is the structure of carbon monoxide. When it reacts with HCl in presence of AlCl3. So this is AlCl3. So by the reaction of carbon monoxide, AlCl3 and HCl, formyl cation is formed. By the use of these lone pairs, carbon make bond with H plus and this Cl is abstracted by AlCl3. And as a result of it, formyl cation is formed. So here you will get CH, triple bond oxygen, and now this carbon will develop this positive charge as it donated lone pair to hydrogen. Now this is formyl cation. This formyl cation acts as an electrophile for benzene. Now it gets attached to the benzene and as a result of it, benzaldehyde is formed. So this is benzene. After electrophilic substitution reaction, this formyl group will get attached to benzene and it results in the formation of benzaldehyde. In the same way, if the toluene undergo Gatterman-Koch formylation reaction, this is toluene CH3 as it is written here, when benzene or its derivative is treated with carbon monoxide, it gives substituted benzaldehyde. So when this toluene reacts with carbon monoxide in presence of HCl and AlCl3. Now you have to attach CHO group to this toluene, and you know toluene is orthopara directing. So here you will get orthopara derivative of toluene. CHO group may get attached to ortho position or it may also get attached to the para position. So here this is CH3 and when it get attached to the para position you will get, so that's how you will get substituted benzaldehyde also. Now come to the preparation methods of ketone. First method is given from acyl chloride. The treatment of acyl chloride with dialkyl cadmium prepared by the reaction of cadmium chloride with Grignard reagent gives ketone. So here, when this acyl chloride treated with dialkyl cadmium, it results in the formation of ketone. So this is ketone and this Cl will get removed with the CD in the form of CdCl2. And this dialkyl cadmium is prepared by the reaction of RMgX and CdCl2. Let's try to understand how this reaction takes place. So this is RMgX. When it reacts with cadmium chloride, magnesium is positively charged and alkyl group is negatively charged, while this cadmium is metal. So again this is positively charged, so it will and there is transmetallation takes place, means cadmium replaces magnesium from RMgX. When two molecules of RMgX react with CdCl2, you will get R2CD. This is dialkyl cadmium. When this dialkyl cadmium reacts with acyl chloride, Cl is removed in the form of CdCl2. So when acyl chloride, this is C double bond OCl, react with dialkyl cadmium. So here again you require two molecules as we are going to remove chlorine in the form of CdCl2. So this CD takes the Cl away in the form of CdCl2. So here CdCl2 will be removed from the molecule and here you will get R, C double bond O and R. So this is ketone. So here you will get two molecules of ketone. Now come to the next reaction from nitrile. Treating nitrile with Grignard reagent followed by hydrolysis yields a ketone. Let's try to understand how this reaction takes place. First of all, draw the structure of nitrile. So if I draw the structure R, C, triple bond N, this is nitrile that we already discussed when we discussed the preparation method of aldehyde. And this is RMgX, so I can take it as given in the example C6H5 MgBr. So this is RMgX. Mg is positively charged, Mg is metal. So Mg is positively charged, so C6H5 will develop negative charge. Here nitrogen is more electronegative, so it will be negatively charged and carbon will be positively charged. So here this C6H5 will get attached to the carbon and Mg will get attached to the nitrogen. Now let's draw the structure. This is R, C, and here you have to attach C6H5 and this is nitrogen doubly bonded to carbon. This nitrogen will get attached to MgBr. Now when this molecule undergo hydrolysis, so after the hydrolysis, this double bond between carbon and nitrogen will break and oxygen will go with a carbon. So here you will get R, C, double bond O, here C6H5, means this is a ketone. So here when you see this example here also, so this is CH3, CH2, C triple bond N, this is nitrile, and here it is C6H5 MgBr. So C6H5 will get attached to carbon and MgBr will get attached to nitrogen in dry ether. So here when this undergo hydrolysis, this double bond will break and oxygen will get attached to the carbon, and that's how you will get 1-phenyl propanone. Now come to the next method. From benzene or substituted benzene. When benzene or substituted benzene is treated with acid chloride in presence of anhydrous aluminium chloride, it affords at the corresponding ketone. The reaction is called as Friedel-craft acylation reaction. This reaction you have studied in the 11th standard. In this reaction, when acyl chloride treated with AlCl3, AlCl3 takes away chlorine from the molecule and leaves carbon as a positively charged. Now this electrophile attack on benzene and undergo substitution reaction. After electrophilic substitution reaction, you will get ketone. So this is the ketone. This reaction is called as Friedel-craft acylation reaction. Now let's solve these examples. Give name of the reagent to bring about following transformation. First is hexane 1-ol to hexanal. So hexane 1-ol is primary alcohol. So this is primary alcohol, and we have to convert primary alcohol to aldehyde. You can use PCC. PCC is a better reagent for the conversion of primary alcohol to aldehyde. Now come to the next question. Cyclohexanol to cyclohexanone. Again cyclohexanol. This is cyclohexane and OH is bonded to cyclohexane. So this is cyclohexanol. And here you have to convert it into cyclohexanone. So here, so this alcohol is secondary alcohol, and here you have to form ketone out of it. So for the conversion of secondary alcohol to ketone, here you have to use CrO3 in anhydrous medium. Now come to the third question. Here parafluorotoluene to parafluorobenzaldehyde. Here you have to convert. This is toluene, benzene where CH3 is bonded is toluene, and at para position fluorine is bonded. So this is parafluorotoluene. Here you have to convert this parafluorotoluene to parafluorobenzaldehyde. Means fluorine will remain as it is and CH3 group is going to convert into aldehyde. So for the conversion of substituted toluene, you can use, so here you can use CrO3 with acetic anhydride. Followed by hydrolysis. Now come to the next question. Here you have to prepare, so this is ethane nitrile, CH3, C triple bond L. This is ethane nitrile and here you have to convert it into ethanol, CH3, C double bond O. So for the conversion of nitrile to aldehyde, you can use double H. So for the good yield, you can use double H for the conversion of nitrile to aldehyde. Now come to the next question. Allyl alcohol to propanol. So here, let's draw the structure of allyl alcohol. So allyl position is carbon, double bond carbon, then single bond carbon. So this carbon is the allylic carbon, and here you have to attach OH. Now balance the hydrogens. So here CH2, CH, CH2, OH. So this is allyl alcohol. Now this allyl alcohol has to convert in propanol. Propanol means CH2 double bond CH single bond C double bond OH. So this is propanol. So here double bond will remain as it is in the product. You just have to oxidize alcohol group to aldehyde. So this alcohol get oxidized to aldehyde. For the specific oxidation of primary alcohol, this is primary alcohol to aldehyde. Here you have to use PCC. Because PCC selectively oxidizes primary alcohol to aldehyde without affecting the double bond. Now come to the next question. But2-ene to ethanol. So let's draw the structure of but2-ene. CH3 single bond C H double bond CH single bond CH3. So this is but2-ene, and here you have to convert it into ethanol. Ethanol means CH3C double bond OH. So here we need to break this bond and add oxygen to it. Means here you have to do ozonolysis followed by the hydrolysis in presence of zinc dust. Now let's solve the in-text question. Write the structures of product of the following reactions. So here in this reaction, when benzene react with C2H5COCl, this is acid chloride in presence of AlCl3. This AlCl3 is a Lewis acid. It will abstract Cl and it generated electrophile. This electrophile attack on benzene and benzene undergo electrophilic substitution reaction. So here let's draw the product. So here this is benzene and the product will C double bond O C2H5. So this is the product of first question. Now come to the second question. Here this is C6H5CH2 whole twice CD means R2CD when it react with acid chloride. CD will remove Cl in the form of CdCl2. And here you will get CH3 C double bond O. This R group, one of the R group will get attached to this CO. So here you will write CH2 single bond C6H5. So here you will get two molecules of the ketone. Now come to the third question. In the third question, there is propane. So here you have to add water molecule to it. So when you will add water molecule to it, you will get CH3 single bond C double bond CH. So OH negative will get attached to the carbon which has less number of hydrogen. So OH will get attached to second carbon and H will get attached to first carbon. When it undergo isomerization, you will get ketone. So here CH3 C double bond O single bond CH3. So here you will get acetone. Now come to the fourth question. Here this is chromyl chloride and H3O plus means hydrolysis. So when this molecule react with chromyl chloride converts aromatic methyl group into aldehyde. So here you will get, this is the nitro group attached to benzene ring, and here you will get CHO. So here you will get para-nitrobenzaldehyde. In the next video of aldehyde, we are going to discuss physical properties.